So we're asked here to factor the expression 12x squared minus 5x minus 2, and then to use that factorization to help us to solve this equation, to find what value x should take to balance this equation. Before we talk about what to do, I'd like to just quickly throw out a question. Why don't we know before we learn something new? How come our existing techniques don't work on this equation? Because what would your first instinct be to do? What's the first thing you try when you try factoring? Yeah, Dylan? Yeah, see if there's a greatest common factor. And if you ask that question about this, what greatest common factor can you find among these three terms? There's none that's interesting, right? Just one. I mean, 12 and negative 2 have a 2 in common, but this 5 in the middle screws that up, right? And because not every term has an x in it, we can't take an x out of everything either. So right off the bat, we know the greatest common factor method is not going to do anything interesting for us. So then what's the next thing that we might try? What will often happen is we'll try to use a technique similar to the one that we used in the previous module to factor this using the sum and the product method. So what does that look like in this example? We'd be looking for a pair of numbers which add together to give me something and which multiply together to give me something. What do you think they need to multiply together to give us here? Yeah, I guess I should clarify. Let's be naive for a moment. Let's try to apply our previous factoring method to this.
Have to equal to 2.
So it would have to equal to,
Multiply by 2 and addition.
add together to give me negative 5. Right, so if I just go straight ahead and try to use the sum and product method to find a pair of numbers which multiply together to give me negative 2, the constant, and which add together to give me negative 5, I can search as long and as hard as I want to, and I'm not going to find such a pair. Because really the only options would be 1 and negative 2 to multiply to negative 2. Those don't add up to negative 5. That's still the case if we change where the sign goes. Negative 1 and 2, that also doesn't work. And those are our only options, because 2 is a prime number after all, so we can only break it apart in a couple different ways, depending on where we place that minus sign. So our previous method is not going to work. The good news is that our previous method wouldn't have worked anyway. We need to not only come up with a method that looks at the negative 2 and the negative 5, we can't come up with a method that just uses these two numbers, because there's a third number that needs to be a part of that process that the old sum and product method is blind to. Right? The method we learned in Module 7 is blind to the existence of this 12 that's in front of the x squared, and it's that 12 that should be our big red flag. That we need a different kind of method here compared to what we knew before. So anytime you have a coefficient that's not 1 in front of your x squared, that's an indicator that the straight up sum and product method is not enough. The good news, though, is that it only requires a little bit of souping up of the old method to make it work with this new kind of problem. So how do I soup up the method? What did you do to get started on this one? Yeah, Gabby.
I multiplied negative 2 times 12.
Okay.
And let that be what P and Q have to multiply together to equal.
Yeah. So very often, and we're going to do more of this later in the course, we'll call the coefficients in this quadratic trinomial a, b, and c, respectively, where a is the coefficient of x squared, c is the coefficient that's the constant that doesn't have an x, b is the coefficient in the middle that's attached to the x. And if I give those names to my coefficients, then the process we want to use begins by multiplying the a and the c together. For that reason, it goes by the name the AC method. Right? That's what your book and your online system call this. So what we do with AC is instead of negative 2, the constant by itself, being the desired product in our sum and product game, we will use a times c So in our example here, that's 12 times negative 2, as Gabby was saying. That's negative 24. And we use AC as our target for what numbers product these two numbers should multiply together to give us. We still want their sum to equal -5, the middle term, but now we want their product to be -24 instead. The good news practically for us is that -24 has a lot of more different ways we can factor it compared to -2. So it opens up a lot of new possibilities, which is important because our old possibilities never added up to -5. So that's where this method gets started. There's another change in how we implement it going forward from here, but that's kind of the important first step in using the AC factoring method. So, now we've posed a sum and a product question. Let's try and answer it. Play the game. What pair of numbers multiply together to give me -24 and also add together to give me -5? Yeah, knock.
21 times -1.
So we could start by trying 24 and -1, but those two numbers add together to give me 23. So I don't want that pair. Yeah, Alex?
8 and -3.
All right, so we go down to 8 and -3. 8 and -3 do multiply together to give me -24, but when I add 8 and -3, I get +5.
So that is -8.
So we're real close, right? All we need to do is put the negative sign on the other one. And then I think we have it. -8 and +3 multiply together to give me -24. They add together to give me -5, and so we have a winner in our sum and product game. -8 and 3. Okay, cool. So now that we've played the sum and product game, in the old method, we could sort of jump straight to a factorization at this point. Under our old method, we would have just said, okay, we got our numbers, so now we can just kind of go x minus 8, x plus 3, and be done. Well, why doesn't that work? If I multiply that out, what do I end up getting?
X squared.
Yeah. I'm gonna get my -5x right. But I'm going to get a 24 as my constant term instead of a -2. And I'm going to get a 1x squared instead of a 12x squared. So unfortunately, it's not as simple from this point to jump straight to a factorization. We've got to put in a little bit more work to do it. So now the question is, in the AC method, what do we do with these two numbers that we obtain when we win the sum and the product game? What did you do with your -8 and your 3? Yeah, back.
Split the x. Split the x.
Yeah, split the x. Split the middle term, the x term. Now, what do you mean by split? What does that look like when you put it on a paper?
Would be 12x squared. No.
So 12x squared, we're going to leave that alone. We're also going to leave the -2 at the end here alone.
And then -8x.
Plus 3x. Yes. So this, by the way, is exactly the same thing as we could have done in the old method when we were kind of looking at it as being the result of undoing a FOIL. So we know that we need to get 12x squared in our final answer. We know we need to get -2 in our final answer. But we don't know how to come up with the -5x because it's going to come from two different squares in this game. So what we're just doing now is figuring out that we're going to be able to factor this if we make one of those squares -8x and the other square plus 3x. That way, when I add up all the terms in my box down here, I'm going to get exactly 12x squared minus 5x minus 2. Okay, but now that we've split this middle term using the winners of the sum and the product game, now what? Now where do we go from there? Because before, we used to already know in this little box down here that we had an x there, we had an x here, and then the winners of our sum and product game went here and here, and so we already knew kind of what was on the outside. But again, that doesn't happen in our example. We don't know that up front. So what can we do? Yeah.
Nothing right, because this equation equals 0, you can split it into 2, and then factor.
So that's our end
Finding
game.
common factor.
Yeah, our end game is that after we've factored it, we'll be able to split this equation into two pieces, solve each one of those pieces, and then we'll have it. But we haven't finished our factoring yet, because we haven't realized the left-hand side as one big quantity times another big quantity. Instead, everything is still individual terms added and subtracted. So we have, I'm going to say, 2 more steps to do before we can get to the splitting. Splitting is the ultimate goal, but we're not quite there yet. So I guess what I'm asking is, how do I decide what goes on the top and the side of this little box down here? So here's how. What I want to do with this grid down here in the lower right is, instead of looking at the whole thing, I'm just going to take the first row. I'm going to look at the first row for a second. First row is 12x squared minus 8x. What's the greatest common factor between those two things? 4x. So what would happen if I tried factoring out that greatest common factor? So the greatest common factor in this row is 4x. So if I imagine that 4x is on this row of my table, then what does that make the top 2 entries? What do I have to multiply 4x by? What should I put here so that the product in that cell is 12x squared? 3x. 4x times 3x gives me 12x squared. Okay, so far so good. And then what would I put here in the upper right? What multiplies 4x to give me negative 8x? Negative 2. All right. So there's something reassuring about what we just wrote. 3x minus 2 along the top of this grid. Why am I optimistic seeing 3x minus 2 appear here? Because it's, yeah, right, it's in the equation. It's also in these boxes down here in the bottom row of the table. So having factored the 4x out of that first row gives us a cofactor, 3x minus 2, by which the rest of my polynomial is divisible. So we can continue playing the game and ask, what do I need to multiply 3x by? What should I place here in order to get 3x in this box? 1. And we can check, and we should check, that negative 2 multiplied by 1 still gives me the negative 2 in the bottom right. So we've just now realized a factorization of this. What does that factorization look like? What are my 2 factors? According to this grid that we have now down here in the bottom right.
4x times 3x minus 2.
4x, I've got a 3x minus 2 over here. What happens with this 1? Can't forget that 1.
4x plus 2.
Yeah, it's the second term in the first factor. 4x plus 1 times 3x minus 2. You can and should double check using FOIL that when I multiply those 2 binomials out, I do get exactly the 4 terms that appear on the line here. 12x squared minus 8x plus 3x minus 2. So splitting the middle term in exactly this way has shown us how to win at the reverse FOIL game. Right? It's seemingly magic. I don't think Alex uses this little grid to explain how the denouement of this procedure. Instead, it does it with a line of algebra that I'm going to add here in a second. So the additional step of algebra that often appears in here is a step that's sometimes called factoring by grouping. I personally find including this step in my algebra to be kind of confusing to somebody looking at this with a fresh pair of eyes. I kind of understand what's going on here, but you might not. So feel free to disregard this line if you feel like this grid is a better heuristic for you. But what the factoring by grouping step will often look like is you'll look at the first pair of terms and the last pair of terms, and you'll factor out their respective greatest common factors, which in the first case is 4x, 3x minus 2, and in the second case is 1 times 3x minus 2. And then from there, you'll use the technique they call factoring by grouping, just to recognize that each of these 2 terms has a common factor of 3x minus 2 that we can bring out and just write once, with its cofactor being made up of the 4x and the plus 1. So, I don't know. I'm of the mind that I like this little square better, because I think it better helps me to explain how we get to where we got on this. But that was the hard bit in the whole process, is the factoring bit. Now that we have the left-hand side completely factored and the right-hand side is 0, which after all, anytime we're trying to solve a polynomial equation using factoring, we need one side of the equation to be 0. And it was for us from the very beginning, so we didn't have to work for that this time. Now we can follow Mac's suggestion, which was split the two factors apart, give each of the factors its own 0, and then solve each of the simpler equations that results. So split this into two pieces. One piece being 4x plus 1 equals 0. The other piece being 3x minus 2 is equal to 0. Now I have to solve each one of those equations. How do I solve 4x plus 1 equals 0? It'd be a two-step process. Yep, subtract 1 from each side, which is going to give me 4x is equal to negative 1.
And then divide out the 4 on each side.
And then divide out the 4 on each side. So 4x equals negative 1. Divide by 4, and I'm running out of room here. So x is equal to negative 1/4. I'm just going to move that whole second equation. X equals negative 1/4 is one of our solutions to this equation. And then the other one is gotten by solving the other factor, 3x minus 2 equals 0. Same set of steps. We're going to add 2 to both sides to get 3x equals 2, and then divide by 3, so that x is equal to 2/3. Whoops. I'll just erase that. X equals 2/3. There we go. And so our final answer, if we could enshrine a final answer here, is that this equation has two solutions, x equals negative 1/4 and x equals 2/3.